Hi, I'm Per Austrin, and this is a presentation of a solution to the problem knockout tournament from the Northwestern European Regional Contest 2017. So in this problem we have n players who are participating in a knockout tournament, and they all have different ratings, and we're particularly interested in player 1, which is Dale Cooper, who we want to help to win the tournament. So in a player, the probability of the outcome of a game is determined by the ratings of the players. So player I defeats player J with probability proportional to Ri. So Ri divided by Ri plus Rj. So the freedom we have, there's going to be like a tournament game tree like this. And the freedom we have is we can choose which of the leaves in the tree corresponds to which player, where each player starts in this tournament tree. And then we want to maximize the probability that at the end, player 1 or Dale comes out as the champion. So the first thing to figure out is how should I organize the players? And here it's intuitively obvious, and it can also be proved, that a greedy strategy works, in the sense that what you should do is you should try to make it so that the players with the highest rating, Dale will counter them as late as possible. So you should try to make those players fight it out amongst themselves, and then let Dale first meet all the players with low ratings, and then just meet a single player with high rating. So you should think of what happens is that you should place all the highest rating players in the left subtree, and Dale together with the low rating players in the right subtree. So basically what you're going to want is you're going to want to sort the remaining ratings. So let's say that we sorted them so that R2 is less than R3 up to Rn. They can be equal. And then R1 is separate. So R1 we don't include R1 in the sorting. And then with this intuition in mind, what we do is we place these on the leaves from right to left. So we place Dale at the very end, and then the weakest among the other players to meet Dale in the first round, and then R3, R4, R5, like this. Okay, so that's part 1 of the problem, figuring out how to place the players in the tree. So now all that remains is to compute, given this layout of the tournament tree, what's the probability that Dale actually wins. So for this, let's define P of Ki as the probability that player I wins game Gk. So the P of, this is game, here I numbered the games not based on the order they happen in the tournament, but like in their natural order in the game tree. So the root game is game 1, then it's the two previous games are games 2 and 3, and so on. So yeah, P of 2, 3 is the probability that R3 wins against whoever comes out the champion out of this game 4. So the quantity we're interested in then that we're trying to compute is P of 1, 1. The probability that player 1, Dale, comes out as the champion of this game 1, which is the root game. So this we can compute recursively as we can consider like all the possible, well, first of all, in order for this to happen, Dale has to win game 3. Otherwise, if Dale doesn't come out as a champion of game 3, there's no way he's also going to go up to the top. So it's the probability that he comes out on top of there times the probability that he defeats whoever he will be facing in the root node. So here, then we can sum overall possibilities. So who are the possible people to meet? Can meet either 3, 4, or 5. 3, 4, 5. And then the probability that player comes out as the winner of game 2, P2x, times the probability that, okay, so this now counts the probability that each term here counts the probability. What's the probability that the root game is between Dale and X? And then we just have to multiply by the probability that Dale actually wins this, which is R1 divided by R1 plus Rx. Okay. So now we have this formula for what we're actually after, and this now gives like a recurrence. So the kind of subproblems we have, now we have to compute similar probabilities for this game tree and for this game tree, and we get similar kinds of recurrences. So this leads to a natural like dynamic programming, which you compute either bottom up or top down. And the running time you get for this, you can analyze it in a few different ways, but you will end up with an order n squared time. And that's about it.